And it looks like we have a couple more students or something.
So just to make it a real democracy, do people have issues like taking the train earlier or doing something that will make it especially hard, other than it's half an hour earlier? Is there somebody that says, I can't catch a train from here easily at 8:30, or this is your opportunity because otherwise it's kind of rolling as a new deal?
Yeah, I mean, if it's a real problem for anybody, let us know.
I saw 2 or 3 smiles saying that's already early enough. So I want to address it because anybody raise it. I'm a good complainer. If I was you, maybe I'll look at that.
He is a good complainer. Okay.
So it's 8:30.
I guess it is, unless I hear a complaint. But you're welcome to register a complaint, and we'll accommodate, we'll keep it the way it was,
Yeah.
if anybody's concerned.
Yes.
If not, it'll make it easier for a few other students.
Is that 8:30 every day, or?
Yeah,
Okay.
we'll just do it every day. It's just too confusing.
Starting
to
Monday?
track. Actually, some of the students have problems on Monday, Wednesday, another student has Tuesday, Thursday, so, the only day we could do 9 would be Friday, I think.
The last on the side announcement is the class website is up only for registered students, so if you're not, you have to email me so I can add you. So you get the announcement if we have changes. So Simon, it spells exactly like Simon. MIT.edu. So see, like the ocean and home. When I was a grad student here, people would call me Simon, and after 4 years of it, I decided good enough. I want to go to my real pronunciation. It's like Jorge. It's hard at the first time, but if you say George, it's completely different. So that's kind of the idea. If you don't need anything from me, you can call me anything you want. But when I was interviewing for classes, that's when I decided to go back to the original pronunciation. So if somehow you're hiding an original pronunciation, I'll be supporting you in this process. So I understand what it is. So is this on right now?
Mm-hmm.
Yes?
Yeah.
Okay. So we'll start the lecture. Today I want to start with a few examples. One is the type of work we do in terms of improvement of process and material selection. And then I'm going to talk a little bit about an example of failure analysis. And then we gradually get into what the class is all about, and we'll talk about castings today. I don't anticipate, it's essentially 45 minutes from now, to give you all you need to understand about castings and go and specify or be able to understand all about it. But I'm definitely going to work on a general overview, and on Monday morning we'll cover 2 key concepts of casting and I'll give you some examples of what it's used for in terms of different technologies, different ways to cast. And then we'll move on to the next processing topics. That's my outline for today and Monday. So the class this semester, I'll talk about processings for about 4 lectures. That's the plan right now. And then I'll talk to you about how the materials behave in service. What are the kind of issues in terms of corrosion, environmental degradation, and mechanical properties that would essentially make it hard to use a certain material for an application. If we think about it generally, because yesterday Professor Eager covered, if we can use gravel, we'll use gravel. The best example at my house, I had the semi-trailers coming in with about 26 tons of aggregate. Each run was $350. And for the same amount of money, I get 1 steel beam delivered, and 26 tons is essentially what they use on the roads to build roads. And the cost of it is mostly to crush it and deliver. Steel is different. You need to get it out of the ore and process it, and that's where the cost difference comes in. So the cost aspect is something that I think you'll get a very good background, and you'll grab a lot of inspiration from the lectures by Professor Eager. What I'll be doing this semester is more talking specifically on how you process these different materials, and also what to look for as to what may limit their use in service. So it should all tie together in that perspective, that you get an idea. Obviously, you want to make it cheap, but at the same time, you need to understand how it's made. So when it comes to, specific application, you avoid getting into problem of performance in service. So it is always a lot of lesson learned that leads to, well, no, we don't use this material underground, for example, or we don't use this material if it's going to be exposed to UV rays and stuff like that. That will limit you in terms of going for the cheaper option all the time. So that's kind of how the two parts of the class, I think, or 3 parts or 4 parts. Professor Eager is also talking about non-destructive testing. So it's all different things, but what happens again is we're trying to cluster a lot of different topics to give you guys a good background, and then there are the online modules to support that. So let's move to the examples. This is a project from about 6 to 8 months ago. Somebody came in and they are building the Xray machines for the check luggage at the airport. So this is essentially paid by TSA to build machines that will get the luggage faster through the conveyor and also detect more information. And one way that they do this is, instead of being a regular CT scan where you rotate around the luggage, they use fixed points for the X-ray sources, and then they scan over and they get the information from that point over a large detector on the other side. So anyway, they need a lot of X-ray sources, and they also need to be able to turn them on and off at a very high rate. And that brings the issue in terms of material. If you're looking, the way the X-ray source works, are you all familiar with scanning electron microscope? Good. So the scanning electron microscope, you have the tungsten filament that produces the electrons, and then you accelerate them in an electrical field. And this accelerated electron is the same thing you can use here to project on a target and emit X-rays. So if in the SEM you use the X-rays to look at the material characteristics, here you use the X-rays for imaging. The only difference as opposed to the scanning electron microscope is a higher voltage. It's of the order of about 200 kV as opposed to 20, 30 that you'll have for a regular SEM. So you can see with this amount of energy that you'll heat up your sample here, which is another piece of tungsten. The reason for using tungsten is everything heats up so much that you want to try to minimize thermal fatigue and oxidation. So what we were working on is essentially preventing the formation of cracks, either in the target here, this tungsten disc, or just right underneath of it. So in terms of design, what you need is something that is this high temperature on the surface, because you know it will heat up. The beam is so strong, there's no way to avoid it. But then behind what you see as the green is essentially a copper block that has internal cooling to try to drag the heat generated from the electrons hitting the tungsten. So this whole system, if you're running it in steady state, you keep providing electrons, you keep generating heat, that's great. But when you start turning it on and off, the surface moves from tension to compression every single time at very high frequency. And that's why they only had a few months worth of life on these sources that, you know, were worth a lot of money, and that was not acceptable. So we got involved and essentially tried to work in not only reducing the peak temperatures. So here you're looking at the temperature. The target is at an angle. The reason is, say the electrons are coming from left to right here, and then they emit the X-rays at an angle, and that's what's used here for imaging purposes. So if you try to minimize that surface temperature here, that's already a starting point. The other thing was to try to make it a little bigger than not, and also in the end to try to not have it all centered. You try to distribute the field so that there's not one hot spot, but it's rather a hot surface. That's kind of the general idea of what I was trying to do. But when you try to do all of this, I mean, ultimately, you can make this much better, but it will cost a whole lot of money. So at the same time, you do try to be reasonable in terms of production, in terms of the material you use, and that's why we were building a model to look at stresses, and at the same time, we were looking into literature data for the material properties. And ultimately, you try to match the best you can the capacity with the demand, the load demand, in this case, the thermal fatigue. And there were two different modes of fatigue. One was when you shut down the machine completely. That's a very large cycle, because you go from that surface that's here at 1,000 degrees centigrade, and then all of a sudden it goes to ambient temperature. And then you have these very high frequency cycles, and depending on the design, the thickness of that tungsten disc that's on the surface, you have the issue with one or the other or both, or you try to avoid it enough that you get the light that you're looking for. So it's not atypical to have to work with the two aspects, the material resistance and what is the demand, and try to get that optimized in detail. So that's an example of work. These are just examples of cracks that you can get on the surface. And if you have a lot of very small cracks, to some extent, it's good because it allows you to accommodate more differential strength. You're dealing with different material. There's copper underneath, it's tungsten on the surface. It's a different thermal expansion coefficient. It's a different temperature. Turns out the copper expands more with temperature, and that's a good thing because it's going to be a little cooler on the back. So that's kind of a way to try to have the physics working for you, where you know the tungsten's going to get hotter, but at the same time the thermal expansion coefficient, so the expansion per degree of heating is less. So you end up balancing things out a little bit. The other projects I want to talk about is these blowout preventers, and that speaks to what happened with the Deepwater Horizon, what happens just about every year in the Gulf or onshore in Texas or Louisiana. They lose control over the well and they have a blowout. Typically, the release of pressure when things starts to flow makes the well collapse. The whole casing breaks and it shuts by itself. The Deepwater Horizon was very unfortunate because there's just so much built-in pressure and resistance through the well that it just kept pulling out, and it kept producing the oil and gas at the same time. So again, a lot of times you'll have a blowout, but it's not as consequential. It's just going to collapse on itself. So what I want to talk to you about a little bit is how we shut those wells. And I have a video. So the trouble is you have this drill pipe here going up and down. And the way you drill is you pour drilling fluid, drilling mud from in the inside of that drill string, and then it goes all the way down to the bit and collects the debris and float them back on the outside, what we call the annulus. So that's the way to essentially get all the rocks, all the pieces, all the dirt out of the system. You screen it, and then you recirculate it back. So if you see a change in pressure in the well, what you need to do is to close this, and that's the schematic here. And it's very high pressure, so you form essentially two different gaskets. There's one closing between the whole housing of that BOP and these ram blocks we call the gray piece. So that's the black ring. So if we look at it from top, you have the hole, you have the pipe, so you need to seal here. And that's what we're seeing here with this sort of stretch donut. That's the rubber. And then you also need to seal in the center between the ram blocks and the drill pipe. It's not the only way to do it, but it's kind of the only way if you're going to keep your drill string. I mean, in the Deepwater Horizon event, they also had another set of these where they were trying to cut the pipe altogether and seal it. So you only have one interface in that case, but that didn't work either. There's always redundancy, but it doesn't necessarily means that you have the time to activate all the devices and it will work. This case here, I worked on maybe 3 or 4 years ago, and what happened, as you can see, the drill string was not in the center. So the first thing that the BOP needed to do was to push it by just a little angle here on these plates that are green and red. It's not all of the design that will allow you to do that, it turns out, but it should be there because there's no way as you work everything that you're always going to have the drill string right in the center. It's also something that did happen in the Deepwater Horizon. There are a lot of government reports that talk about all the things that went bad. One of them is they realized they had flow and it was flowing a lot. So if you have flow here, it's very hard to seal with the rubber. You're going to erode the rubber very, very, very quickly. When I said high pressure, these things are rated to about 15,000 psi. By comparison, the water pressure in a home is typically 60 to 80 psi. So you're talking, 100 times that at least, depending on the scenario. It's not easy. You can't just use rubber. And that's why in that schematic, all the rubber you see is embedded in steel. So it doesn't extrude right out. When you close right here, you have the green and the red plate holding things together, just like that. And the rubber is facing each other, the elastomer. It's a relatively complex formulation that allows you to deal with high temperature and you maximize the erosion resistance. You touch at this, you can't necessarily tell it's rubber. It's so hard. And I can bring some pieces to on Monday like that. Continue the discussion. But essentially, the elastomer in this case is a very important part of the design in terms of minimizing the erosion and still getting that seal. When the two pieces of a little worn out rubber face each other, they need to be able to completely hold the mud. If you start having some mud going through, it's gone because it will continue to leak in that area and you consume the whole elastomer, and that's what we see after the fact. We see a few pieces of metal left and a lot of erosion. And so again, some mechanical properties for the elastomer and mostly the environmental resistance. If there's going to be some hydrogen sulfide in the well, that's affecting the resistance and the degradation of the elastomer at high temperatures. So you have a lot of things to take into account if you're going to make a change. So, and what we've seen in the past is people making changes, just saying, well, it looks the same, or it doesn't look the same, or it's good enough. We tested it. But if you test it just as closing it, and then you put the pressure, it's very different than when you have some flow and then you try to activate it. The speed and the quality of the match is a lot harder, more important in a dynamic situation than if you don't have it before. So that was the example of, you know, going after the fact and finding out what didn't happen correctly. Structural materials is obviously my passion. That's what I do for work. So we can go on and on and on. But I'm making a list of how I see things. You know, there are different ways always to look at such a large and generic topic. But in terms of going and actually designing stuff or servicing it, rehabilitation, failure analysis, the processing is always important. The way things are put together, whether it's cast, whether it's a rod product, you end up, whether it's joint, you end up learning a lot, you end up trying to, you can already anticipate issues if you know how the material is being processed. How it's processed is affecting the structure, and we'll go into that in just a few minutes. And then you get into a lot of properties. Is it crack propagation resistant? Is it going to resist the environment? That's the last part of the class here. Material selection is, I think, comes in when you understand all of this. When you understand all of this, now you can go and say, I'm going to try to minimize the cost. But it's not just, oh, I can get it cheaper. You know, how long is it supposed to last? It's like plumbing system. We say up to 50 years, depending on, you know, if it's commercial, residential, and what have you. So you can't just run a simple test and say, well, yeah, it's holding my 60 to 80 psi pressure right now, so I'm going to use this. You need to run some accelerated degradation. You need to run some high temperature tests to predict what's going to happen in, say, 20 years. And that happens a lot with buried structure. Polyethylene pipes for, you know, natural gas and distribution, where you can only run a test that would, you know, there's a standard test that runs for about 4 months, and then you use that for a very long life. But you have to run it at high temperature, and it's still very expensive. You know, a lot of times they try to make changes and not do that test, because otherwise it's going to, you know, start production into the next year. So it's very difficult sometimes to make improvements in material formulation because of all the long-term implication that you don't necessarily know the effect unless you're willing to wait for a period of time. There's a module that I gave 2 years ago, and we will get the website running as far as the live lecture. It's not working right now, so don't even try it. But whenever it's working, I'll send the announcement with an email to everybody, so you can get a little feeling for what's out there. And there's a lot of it. So some of these topics come into 12 modules, the same way that this semester we're pretty much dealing. Professor Hager is doing material selection, and I'm doing probably mechanical properties and physical properties, if you take the environmental as part of the physical properties, and a little overview of processing. Everything else, life assessment, dealing with cracks and details, there's a whole module on that, essentially, if that's something that's interesting to you. Let's see. Okay. So demand capacity, that's what I came to you with the introduction when I was talking about the Xray Source design, where you want to try to get a match. So this is a way that I always use to you know, do work. Are we unsure about what the load is going to be, or are we unsure about how good the material is going to be? And that's where you always have to think about it both ways. And that's where a lot of people in our field of consulting have a problem, because if they have a mechanical engineering background Well, they know the demand. If you're really a pure material science and you've done a lot of processing and looking under the microscope at what it looks like, you know the capacity, you know, but then ultimately you need to meet both, and then you start talking about cost. You know, you start trying to optimize other aspect than just the engineering performance. We've covered already what we're going to talk this semester. So, casting. I want to say it right up front. I think most people know castings are not of metals are not the most common parts that we see on. Most of it is being cast and then processed to blend the microstructure and get the different shapes that we want. It's relatively rare, especially for high performance parts, that you will just take the melted metal, throw it into a mold, and here's the part. It happens in aerospace. We use a lot of aluminum and aluminum castings until, you know, I don't know if they always try, but until recently anyway, were only secondary structures. You can't use it as part of, you know, the fuselage or the main frame because you don't know exactly the properties. You can't design it to the limit because there's going to be a lot of variation. This example I'm throwing in is one example where you can use it. It goes on an ATV, and the ATV, a utility vehicle, I've got some images of it if you're not aware. Weight is important, but at the same time, you don't want this to go flying. It needs to have weight. It's not flying, so you can afford to put a little extra material here and there so it can take hits, and it's not the level of optimization as a commercial jet. A lot of stuff is oversized. So that component that I showed in the previous image is the knuckle here that essentially attach the wheel and connects to these control arms to hold the wheel in place. It's a cast aluminum because you can get a very nice complex shape in just one operation. You make the mold and you pour it in, and if you're willing to make it bigger, that means your stress demand is going to be low on that part, and you're good to go. Ultimately, they do some machining after the fact to be able to put these bushings in and to put the bearings. But here you have reinforcement ribs, and you can make it a very nice shape and smooth to avoid geometrical stress risers that will happen. You know, you could maybe make this with a straight bar, a flat bar with a round bar, and weld the two together and make it out of steel and be done with it. But in this design, everything has the curvature, the rib reinforcement, it's all smooth. So there are a lot of advantages of doing it that way in certain applications. So with that very little introduction, when you take the molten metal and you throw it into a mold, the mold is always cooler. Otherwise you won't, well, there may be an exception when you do single crystal for turbine engines where you really keep everything molten and you control the solidification very, very slowly. But in general, you take very hot metal and you pour it in, and you essentially rapidly form a solid, so there's solidification at the interface with the cold mold, and you typically end up with multiple types of structures. So the first one is, we call it here chilled crystals. There are different names for it. That happens very quickly, and then you have a growth of the solid that is more oriented these columnar grains, and we'll explain why later today and on Monday morning. And in the center, everything that's left will eventually solidify as a single piece. So this is typical, and I've put on here an example here of a billet that is not exactly, black and white. as the schematic I showed you, but that's how life is. These billets, there are a lot of ways to try to minimize forming these large elongated grains, the columnar grains. So in the process, and I think, yeah, I've got a processing image here. So we don't really have steel mills around here, but when I grew up in Canada, we did. So one of my friends was working there for the summer, and I got to see a lot of that stuff. It's very impressive because it's hot. The steel is so hot, it emits a lot of radiation, so even if you're far away, you feel it a lot. You don't need a heating system in these shops. It's just, even in the winter, it's comfortable if you're close to the process. So essentially, and what I'm showing here is continuous casting, which is very, very common. So you prepare a heap of, say, a steel alloy that you want to manufacture. It's in a big container, and you will adjust the chemistry to exactly what you want. So when people look back and something failed and say, well, maybe it's the chemistry that was wrong. It's possible, with a raw product, it's possible that they made a mistake, but most of the time, they control it very tightly, because if there's a problem, they can always adjust the chemistry of that big molten pot. And then they start pouring it. And they pour it very regularly, it goes into these molds, and the billet just starts solidifying as you're going down. Typically it starts vertical, it turns around. And one thing that I wanted, it's a relatively old technology, 100 years type of deal, but at the same time, people still make improvements. So in terms of getting these columnar grains growing, one of the things that was new at the shop that I was at is they were putting on a magnetic field that was strong enough to spin the liquid inside the billet to break these grains, to essentially minimize the finger growth of the metal into the alloy. And it may look like a small change, but for them it was big, because if you don't do that, you end up, and we'll cover that later, you end up with a chemistry in the center of the billet that's different from the edge. Because when the liquid solidifies, it's harder to fit impurities into a solid than it is into a liquid. And therefore, impurities and also alloying elements are going to be pushed towards the center. So the more of that segregation you get, higher concentration of elements in the center that are not steel, but iron, for example, the more processing you need to do at high temperature after the fact to try to blend it back so it diffuses back and everything is becoming the product that you were hoping to get. So that's, in a nutshell, how you do this continuous casting. You can do these big billets, but you can also do sheets. If you're going to make aluminum foil, you're hoping you don't start with a billet that you manufacture this big. They will still do it sometimes, but if you can make a plate, a strip, you don't have as much thickness reduction to do down the road. So these are two main ways to go from the molten metal and process it in a billet as a continuous process. So I've already started talking about what you're trying to do here. You're trying to get the best structure, and a lot of the physics is not really working for you. The metal wants to separate. And you have some familiarity, I guess, with phase diagrams, right? And I'm showing you here the iron carbon phase diagram in the concentration. So here on this side, it's 100% iron, and around here you have 7% carbon. If you're going to take, traditionally, cast iron was relatively popular for the reason that if you go right here, at a concentration about 4 1/4 carbon in iron, your liquid will remain at up to the lowest temperature in this whole diagram. So pure iron is going to melt. You'll have to heat it up until above 1500 centigrade before you melt it. And if it's got carbon in it, you can get that down to about 1200 centigrade. So it's a significant difference when you think in terms of technology. It's very hard to have molds that will hold material at super high temperature. The lower the temperature is, the easier it is to have refractories that will hold your molten metal, and the amount of heat you need is less. So there are a lot of advantages to adding carbon into steel to be able to melt it more easily, and also when you cast it into molds, you don't have as much of a temperature drop. And that's the concept of eutectic or eutectic composition. So the eutectic, when you have a two-phase alloy, is the lowest point in composition where you'll go straight from a liquid to a solid. It's great because if you have the exact eutectic composition, you wouldn't have all that segregation issues and these things that I was talking to you about, because you essentially, in terms of the thermodynamic, the whole alloy is perfectly happy in the liquid state with that iron and 4 or 5% carbon. And then from one temperature, as soon as you go across it, everything wants to become solid. Yeah, but it will separate. It will separate in this phase here, so an iron-rich phase and a carbon-rich phase, but all at the same time. So it's a way to minimize the segregation also, but it makes for a relatively brittle material because you put a lot of carbon into it. You have a phase that's very brittle, and that's why cast iron has a lot of limitations. There are ways to